So now let's see if we can take a closer look at the power that is absorbed by the device in a switching power supply. And in particular, we're going to look at the average power dissipated. And so what we're going to do after we develop an equation for our average power dissipated, we're going to look at an example in a later video that compares our switching power supplies to our linear power supplies, and we're going to see just how much better we can get our efficiency by using these switching power supplies. Okay, so let's start by writing a general equation for our power dissipated. So our power dissipated, we're going to say, is equal to our switching frequency, which I'm going to write as F sub S, times our total energy dissipated, our U total. And so I'm using U to be consistent with our textbook's notation. And so again, this part of our class, our power supplies, is coming from our Neiman textbook. So our F of S is our switching frequency, and this is our total energy dissipated. Okay, so why do we have this frequency term in here? Well, if we remember, the basic operation of our switching power supply is we have this sort of switching cycle where we switch on, we switch off, we're off, and then that just keeps repeating over and over again. And so remember, this is occurring on very small time scales, typically on the order of milliseconds or sometimes even smaller. And so what we're interested in then is this switching cycle that's occurring between here and here. And so this is just repeating over and over again. And so what we can see is we can actually break this down into our subsequent parts. And so we're actually going to ignore this T off part, because as we see for our T off, our power is 0. So that means we're going to have 0 energy. So we're not going to worry about that, but we can look at these other three and we can say really this U total, so I'm going to have our F of S here, really this U total is the energy during our time that we're switching on, the energy of the time that we're on, and the energy in our switching when we're turning off. So from left to right, that's our left, middle, and right sections here. So we can look at the energy in each of those three regions separately. And so we're actually going to talk about a simplifying assumption here in a little bit, where really we're just going to consider sort of two calculations and combine those two and bring them back to this equation here. Before I do that, I just want to define our switch waveform period. So of course, if we have a frequency, we can also define a period, in this case T of S. And so T of S is going to be equal to the sum of those 4 times. So the time for our switching when we're turning on, the time that we're on, the time when we're switching off, and finally the time when we are off. Okay, and this is our switch waveform period. And so that's just the area in between the area that's highlighted in yellow in the waveforms above. Okay, so coming back to this equation 1, we want to simplify this a little bit, and I'm sure you're going to be surprised to hear this, but we're going to make an assumption to make things a little easier. So as I keep saying, a lot of what we do in these higher level classes is, if we're not using some type of simulation or calculation tool, we can make some simple assumptions that make our answer a little less accurate, but it's going to make it a lot easier while we're doing these sort of first order calculations. So what we can see is, if we assume that our two switching times are about the same, so if we assume TS on and TS off are the same, we can just generalize that as switching time TS, and then we just have to find that energy one time. So let's say we have a simplifying assumption. Okay, and what it is that our switching time when we switch on is equal to our switching time when we're switching off. And so that's not necessarily going to be the case, but again, it's going to give us a good first order approximation. And so let's call this generalized switching time TS. So now we don't have to look at both of these transitions, but let's look at our off to on transition. So let's say we're going to consider our off to on transition. And so coming back up here to our plot, we're looking at, let's get rid of this line. We're essentially just looking at this area here. And we're going to be focusing on our current and voltage, and then we're going to come back and, of course, as you might guess, multiply those to get our power. So we want an expression for our voltage. So we can write an expression for our voltage as a function of T is V max times 1 minus T over Ts. So let me come back up to our plot for a second and label a couple things, or point out a couple things that I've already labeled. So notice right here, I've said sort of arbitrarily that this time is 0. That's the start of the switching waveform that we're considering. And then I've said this time Ts is after we've switched. So Ts is the amount of time it takes to switch. So that is our Ts there. So what we're saying with that equation is we're starting at V max at t equals 0. And then it's saying that we're going down to a value of 0 at Ts. And so essentially we can think about this because we're just considering the energy in the switching. This V min is really just kind of an offset, and we're going to consider that when we look at the energy in this middle region where we have T on, when our device is on. So that's the reason we don't have a plus V min offset coming in there. Okay, so now our current is going to be similar. We can say our I of T is equal to I max times T over Ts. And so in this case, we see that the current is going to be 0 when T is 0, and the current is going to be I max when our T equals Ts. And so coming back up here to our waveform, for our current, we can see that is exactly what is happening between our two highlighted bars there. Okay, so now if we want to relate this to power, we can do that, but remember we had our previous equation in terms of energy, right? So we had our power dissipated up here in terms of the frequency and the energy. So let's write a more general relationship between our power and energy. So in general, we know that our power is the time derivative of energy. So again, I'm using capital U for energy just to be consistent with the text. So we have du dt equals P. Well, we can sort of separate and integrate to say that our energy is equal to the integral of power dt. And then we know that our power is just current times voltage, so we can say this energy is equal to IV dt. So we can now plug in these two equations here, and we get that our energy for our switching, because remember all of this is just considering one switching transition, we're considering our off to on transition. So the energy in that switching is V max and I max come out front because those are just constant values. And now we have the integral from 0 to Ts because that's sort of the time frame we're considering. And our voltage was 1 minus T over Ts, and our current was T over Ts, and then we just have our dt. Okay, so that's kind of messy. So we can make this a little easier by doing a trick, sort of a substitution. So let's say instead, let's change our variables and say, let's let x equal T over Ts. And so if we do that, we need to, of course, the reason we've chosen that is we look here, we see we have this T over Ts and T over Ts. But now we're going to have to address two other things. We're also going to have to address this dt as well as this Ts here. So what we're going to do, let's talk about what our dt is first. So if we sort of multiply our Ts by both sides, we can see our dt is going to be equal to Ts dx. Okay, so let's sort of take all of that into account and update our equation again. So we're going to have our energy in the switching is equal to V max I max integral. And so we were starting at 0, so if we had 0 for t, we can look at this here, and we can say 0 for t corresponds to a 0 for x. If we put in a Ts for t, and the reason I'm saying Ts is because we have Ts as our upper limit, so Ts for t corresponds to Ts over Ts, which is just 1. So we have a limit of 0 to 1 now. And again, we just said, of course, the T over Ts becomes X. So now we have 1 minus X times X. And this becomes dx, but we also have a Ts, which the Ts is going to be constant, so I can just pull that out front with our other constants there, Ts. So now it's just a matter of doing that integration, and so I'll just write down what that integrates to. So of course we would just separate, we can multiply this through, we have x minus x squared being integrated, and we can do sort of each of those on their own. So we have Ts, Vmax, Imax out front, and then that's multiplied by x squared over 2 minus x cubed over 3, and that's evaluated from x equals 0 to 1. So we do that, and we find that our energy U of S is equal to T of S, Vmax, Imax, divided by, let's try not to go through everything there, divided by 6. And so this equation, we're going to call equation 2, and ultimately what we're going to be able to do is substitute that in for our energy in our off and on switching time. So that leaves us with needing to find this energy for our on time. And so this is actually going to be a lot more straightforward, because if we come back and look at this area here, so let me change this. Oops. So now we are looking at this region between our highlighted bars here. So we can see we just have constant I and constant V, so that's going to make our life a whole lot easier. Okay, so now we need to consider, so let's say this, let me go ahead and say explicitly, this is, we're saying the same for our off to on and our on to off transitions. Okay, so now we want to consider though, while the device is on. So while our device is on, we simply have the energy is equal to the time it's on times the power, which is V min times I max. And so let's call this, and so let me put this in blue just so it stands out. So this is equation 2, and this is our equation 3. So essentially now what we want to do is we want to substitute these two equations. So we want to take 2 and 3, and we want to substitute into 1. So we're taking this US and U on, and we're putting it up into this equation here. So let's go ahead and do that. So now we have that our power dissipated is equal to our Fs times T on V min I max, so that was for our I on, that's from equation 3 right there that we can still kind of see. And then we're going to have our two equations, one for switching on, one for switching off. And so we're still assuming that they're on, but I'm going to write them as sort of two separate times, just so we can see clearly. The form will change a little bit if we don't make that simplifying assumption, but again, this is going to be a good enough approximation. So we have Ts on Vmax Imax divided by 6, and then we also have one for Ts off, so we're going to have Ts off times Vmax Imax divided by 6. So we get something that looks like that. And so we can actually notice that we have Imax in all of these terms, so we can factor that out, and we can get that our P dissipated is equal to our switching frequency times Imax. And then in parentheses we now have T on times V min. Okay, V min, and then plus, let's combine these two into one. We have Ts on plus Ts off, both of which are being multiplied by our V max, and both of which are divided by 6. So there's sort of our simplified equation for our average power dissipated in these switching power supplies. So what we can notice here is we sort of have these two major terms, And so depending on what type of operation we have, typically one of the other will dominate. So let's look at each of those two. So we have, so this term here, of course, represents when our device is on. Whereas this term here is representing both of those transition periods where we're switching. And so again, depending on the exact conditions, particularly our Vmin, our T on, our switching times, our Vmax, one of these two is typically going to dominate. So one will usually dominate. So then just a couple design notes. So we can look at this equation as we're sort of trying to design a circuit. So let's say we want to design something that's going to have low current and high voltage. So if the system we're working on has low current and high voltage, we can come up here and we can look at this P dissipated equation and we say, okay, well, our I max is going to be pretty low and our V max is going to be pretty high. So in that case, we want to have our fast switching. So we want these values to be really small to counteract our large V max. So for this case, we would want fast switching to sort of counteract that large V max and keep our efficiency high. So on the other hand, maybe we have a system where we have high current and low voltage. So if we have high current and low voltage, so now we have this I max term out front is very large. So of course we're concerned that's being multiplied by everything, but we know our V max term isn't going to be as large as it was the last time. So now what we want to do is we want to focus on this V min and we want to try to keep that as low as possible in our design. So in this case, we want to make our V min small to improve our efficiency. So that's sort of the basic idea. One other thing I have in the notes here that we want to mention, just wasn't brought up at the same time in the textbook, but I think is relevant to see now, is our fractional switching duty cycle. So fractional switching duty cycle. And so that is defined as D sub S, and it's equivalent to our TS on plus T on divided by TS. And so that TS is the switching waveform period that I defined earlier on in this video. This is another instance where certain textbooks or certain people might define the fractional switching duty cycle a little differently. So just be aware, in this case, we're only talking about including that switching period when we're switching on. We are not including the time when we're switching off. So what we're going to see in the next video is an example. We're going to put this equation for our P dissipated to use, and we're going to compare explicitly a switching voltage regulator and a linear voltage regulator. We're going to see sort of how they stack up to one another, and then after that we're going to go on to look at some specific topographies for our switching voltage regulators.